Okay. So, good morning, everybody. It's a real pleasure to come back here in the Aula Magna of CNR for the Christmas lecture that we had online, and last year we had to cancel at the very last minute. And for this year, I'm very happy to introduce you Professor Monica Colpi. I think there are not much words to say about who is Monica and what she did, but in a very rapidly, she got the PhD in Milan. I don't say when, because it's a detail which is not needed. And just to give the context, her first postdoc was in Cornell, working with Shapiro and Teulkowski, those that wrote a textbook which is very famous. And then she moved to Sissa and then back to Milano, where is full professors since many years, and where in the recent 4 to 5 years, she was able to put together a very strong group of young scientists, mainly working on gravitational wave, but not only. Today, she will talk about the low-frequency gravitational universe with Lisa. Monica?
Thanks, Andrea. And so, okay. So thanks for the kind invitation. I'm really very pleased to be in Bologna in front of esteemed colleagues, friends, and also young students. And I feel a bit embarrassed for this, but I am also happy to tell you about the low frequency gravitational universe that we will be unveiling for the first time with Lisa. We had problems in forwarding the slides. I tried before. No, okay, well, maybe I do with my iPad. So here's the outline of my talk. I would like first to introduce to you gravitational waves. It has been really a challenging and intellectual effort to understand whether they are real or not, the detection principle, and then Lisa. The Laser Interferometer Space Antenna, the first ever mission that will observe in space the universe, the sources that are emitted from below 0.1 millihertz to around 1 hertz. In the second part of my talk, I will describe the prospective sources and the science objectives of Lisa. And I want to say that our ability to create a science case has been guided by our deep knowledge about the electromagnetic universe. We have seen black holes emitting over all wavelengths, and that inspired a lot, as well as the possibility of detecting also primordial backgrounds. And then I will touch upon two themes I'm very fond of: the Lisa synergy with Einstein telescope, because I really hope to in future to see that to prove the universality of black holes over a mass range that is covering more than 8 orders of magnitude from the stellar to the supermassive, and to try to unveil the origins of high redshift quasars. And then I will touch upon the multi-messenger astrophysics that we will be carrying on with Lisa. So let me take you back in 1916, the year before Einstein discovered the equation describing gravity as a manifestation of the space-time curvature, space-time warped by the mass and energy content of the universe. And the year after, Einstein was immediately trying to see whether within his equation he could derive radiative solutions. being aware of the difficulty in finding these exact analytical radiative solution due to the nonlinearity of Einstein equation. If you think at a propagating perturbation of space-time, which is carrying energy and momentum, energy is a source, and thus also the wave is being modified. We don't have this analogy with Maxwell's equation. And so immediately decided to work in the weak field limit, imagining that you have a perturbation, a vibration of space-time propagating over a flat space. But what he found that three radiative solutions were unphysical, as they could be removed by a suitable choice of the coordinate system. And in an exchange with de Sitter and Eddington, they were very critical, and Eddington say, well, gravitational waves propagate at the speed of thought. So Einstein for a long time casted doubts on their existence, and then retreated back when we found a cylindrical wave that could transport energy. Einstein passed away in 1955, and Bondi, Pirani, Robinson, and Feynman met in a workshop at Chapel Hill that was fundamental, because in their discussion after all, they end up with two key papers, one by Pirani, who was able to demonstrate that when gravitational radiation is present, the gravitational energy flux, so the energy flux, cannot be removed by a local Lorentz transformation, by a boost. So this means that if gravitational radiation exists, it has to propagate with a speed which has to be universal. And in general relativity, there is just the speed of light. And Bondi, Pirani, and Robinson later on showed that the passing of a wave produces a relative acceleration on test free particles, and as such, waves transport energy. And this is a seminal paper because it's telling us how we can detect gravitational waves. For us, it's now very simple. What a gravitational wave is? Well, it's a tensor perturbation of the space-time metric, traveling with speed equal to the speed of light. It carries two independent degrees of freedom, which we call polarization states. And we know that the warping action is transferred to the propagation direction of the wave, as much as electromagnetic waves do. But contrary to light, gravitational waves propagate almost undisturbed due to the weakening, the gravity is a weak interaction. But they may be subjected to lensing from weak or strong lensing, and are affected by the expansion of the universe. So the frequency of a distant source is going to be redshifted. Einstein in 1916 was able to infer which are the sources of gravitational waves, not a dipole varying field, but any time varying mass quadrupole moment. And it is clear that the wavelength is larger than or comparable to the system dimension, because the gravitational waves are monitoring the dynamics of an astronomical system. So we cannot have an image, but we can just listen to the sound of a gravitational wave. The amplitude, frequency, and even most importantly, phase carry exquisite information of the source physical parameters. So the message I want to give that we can carry on really precise measurement about the masses and the properties of the sources, and the back of the envelope calculation is showing that the amplitude h of the gravitational wave is linear in the mass producing the wave, and is depending on the square of the velocity of any non-spherical motion divided by c square. So it means that if we want to have a large H, we need sources whose dynamics is extremely relativistic, as it is the case of the merger of two neutron stars or two black holes of arbitrary mass. But what is also interesting to note is that H, the quantity that we are going to measure, is scaling with 1 over the distance, the luminosity distance. And so if you have an experiment that has sufficient sensitivity, then we have access to almost the entire universe. Light scale, instead, fluxes are scaling as 1 over r squared. Well, following the discovery of 1913 plus 16, the double neutron star binary, for which we had indirect evidence of gravitational waves, many astronomers and physicists made a serious effort in studying and exploring the post-Newtonian expansion dynamics of the sources, and also to study the properties of the waveforms, that is, the properties of radiation in the far field when we detect, because they are our, we extract information from the waveform. And there is also an important boost on numerical relativity, especially in the last 20 years. And so now we are able to solve numerically with a high precision the Einstein field equation, in particular to describe the merging of two black holes, as I was highlighting in these two, moving, one in vacuum and one in magnetized plasma. Well, detection. It's relatively easy to show that when you have a monochromatic wave, it is, and you have, as it is in this figure, an annulus of test masses in free space, then the passing wave, which is orthogonal to the plane of my screen, is imprinting changes in the proper distance. The proper distance is a scalar invariant between the various test masses. The displacement is linear in the perturbation and is as long is the distance between the test masses. And just in this figure, you see the stretching and squeezing associated to the two polarization states. So you can view a wave and an oscillating tidal gravitational field, which is just stretching and squeezing these test particles. But also rulers are stretched as test masses are. So how can you carry on a geometrical measurement? Luckily, light follows a null geodesic. And so just imagine you have two of these free test masses that are exchanging laser beam coherent radiation. Both test masses can be as emitter and as receiver. And if you just focus on one light cycle, then you can compute the time it takes light. And in absence of a gravitational wave, it's just 2L over C, where L is the separation between the test masses. But in presence of the wave, you have a modulation at the frequency of the wave. And the best way to catch and detect a gravitational wave is to let the two test particles to ride. So you need a distance that has to be comparable to the wavelength of the gravitational wave. Add a third test mass, and this is almost LISA, because then you can create 3 links and you can fully measure the polarization state of the passing wave. The only difficulty is that gravity is everywhere in the universe. So I don't have free test masses at rest. but we can have free-falling test masses in the gravitational field of the sun. And so if you imagine to have your test masses protected by a spacecraft that shield them against any external non-gravitational disturbance, and you imagine that your test masses are just cube of platinum and gold of just 2 kilograms in weight, when this is LISA. So LISA is a constellation of 3 drag-free spacecraft, which are at the corners of an equilateral triangle, each side 2.5 million kilometers long, which is equivalent of saying that we will be able to detect gravitational waves at the peak of the sensitivity, which are just a fraction of an astronomical unit, with a sensitivity which is broad enough to see a variety of sources. LISA is on an Earth-trailing heliocentric orbit because we really need free-falling test masses in the gravity field of the sun. They are at about 60 million kilometers away from Earth. And since they are rotating, as it is shown here, around the sun, our baseline is 2 astronomical units, and this would help sky localization. We expect a 4-year lifetime plus extension up to 10 years. After 10 years, the constellation is losing the being a nearly rigid equilateral triangle, and so the test particles that are following purely celestial dynamics will come away one relative to the other. LISA is going to measure the temporal changes in the proper distance of these free-falling test masses with a precision at the picometer level. So the displacement of the wave will be of this order. And this is possible because thanks to the heritage of LISA Pathfinder, we have been able to place in space this test particle, and we were able to measure and mainly reduce spurious accelerations down to 5.2 femtometer per square second per root hertz. So LISA Pathfinder was sensitive to a single collision of an atom onto these cubes and have a control on the acceleration in order to measure then the true gravitational wave passing away. We have 2 test masses in each spacecraft to guarantee 6 links in order to have a simultaneous measurement of the 2 polarization states. So LISA is an almost all sky monitor, and in reality what we'll be measuring is the temporal oscillations in the beat frequency mode at each test mass, which contains the true wave plus stray acceleration and laser and shot noise of the interferometers. It was in the 70s that LISA was already conceived as a space mission, but the conceptual design came solid around 1990, and LISA was proposed by ESA as a cornerstone mission for Horizon 2000 plus. And in 2001, NASA joined ESA for 10 years, but in 2011, NASA had to turn down in order to complete the construction of JWST. And so ESA ran alone, and with some of you in this audience, we were in Paris. It was January 13th, 2017. When we proposed LISA as a 3rd large mission concept to ESA, and in June of the same year, LISA was selected thanks to the outperformance of LISA Pathfinder that really demonstrated our ability to have free-falling test masses in space. And the enormous momentum that the discovery of 150914 had on the community. We detected directly the first high-frequency gravitational wave from binary black holes of stellar origin. We didn't know their existence. We could really prove that the black holes are really not candidate, but they are consistent with general relativity, with no relevant evidence of deviation in the residual noise. And with the discovery also of 170817, the double neutron star, for which also we had the electromagnetic counterpart, we could measure the speed of the gravitational wave with a precision in 1 part to 10 to the 15. And this is just the beginning of a new era of exploration of the high-frequency gravitational universe. LISA is about to be adopted in the end of the incoming year or early 2024. We are just checking our cost cap. So let's come to science. The science case and the key questions we would like to address. But in order to do this, let me just have a little digression, because most of our sources are binaries that carry a time-varying quadrupole moment. So if you consider binaries circular in two test masses in circular motion far from coalescence, to leading order, the frequency of the gravitational wave is just twice the Keplerian frequency, which is depending on the total mass of the binary and the semi-major separation. If the two test masses, the two neutron stars or the two black holes, are sufficiently close, you could also detect what we call the chirp, that is the change in frequency, which is rising as the two particles are coming closer and closer, which is depending on the so-called chirp mass, which is a combination of the reduced mass of the system and the total mass. And once we have also the amplitude, we can identify the binary, whether it is a white dwarf binary, neutron star, or black hole. But when we consider a system at coalescence and we consider black holes, then the minimum separation is the size of the event horizon, which is scaling as m. And so the frequency during the merger is increasing and costing to a stable value, which is linked to the inverse of the total mass of the binary. So if you have a binary of 10 to the 6 solar masses, well, the peak of the emission is occurring around a millihertz, where LISA is highly sensitive. So we can detect the inspiral, merger, and ring down, that is the oscillations that the new black hole have in order to get rid to any known asymmetry and become Kerr according to general relativity. What is amazing that the energy that is emitted in this merger is about 10% of the reduced mass. And if the particles or the black holes have comparable mass, this could be 10 to the 4 mc squared, so a huge energy. And at peak, the luminosity is around 10 to the 56, 10 to the 58 ergs per second. This is independent on the mass because energy and time have the same units in geometrical units. So it will be an enormous amount of energy which is released. The information we extract comes from the so-called waveform during the detection. And if you have spinning black holes, spin are introducing precession, and so they are shaping the waveform. So this really helps in estimating 15 parameters So it's characterizing the source out of 2 degrees of freedom we have. So there is an intense analysis which is required to extract the physical parameters of the source. Let us come to LISA science. I invite you to read a suite of reviews we have been publishing on Living Reviews on Relativity. And let me just start with the sensitivity curve of LISA. This is a plot where I'm showing the characteristic strain versus frequency. And this line I'm indicating is just the sensitivity of the observatory. So all the sources that are above this line could be detected by LISA. And let's have in mind that the characteristic strain that LISA will be able to detect is of the order of 10 to the minus 20. 10 to the minus 21 was the strain of 1905, of 1509-14, the first source of gravitational waves. So imagine that LISA is launched. We have 1.5 years of cruise to reach the orbit, 6 months of commissioning, 6 months of early data taking. And what we believe that the first sources we are going to see are unknown double wide dwarf binaries with periods of minutes that are really emerging loud. These are monochromatic sources. We expect them to emit at twice the Keplerian frequency, and we have to wait about 6 months to exploit the motion of the constellation to see the Doppler drift of the line to identify these sources. In about 6 months, also, we hope to detect known binaries, the so-called verification binaries that live in the Milky Way. They are ultra-compact X-ray sources or AM Vanaticorum sources. So here we are doing simultaneously multi-messenger, because we see in optical in X-rays, and also we can validate the data analysis that we will be doing with LISA. We have a foreground, a galactic foreground. Most of the sources are in the Milky Way or in nearby satellite galaxies, but there is a foreground resulting from millions of binaries that are producing a confusion noise with an amplitude which is modulated by the constellation, and in a sense is corrupting a bit the sensitivity, the nominal sensitivity. And so initially this background will pop up, and there maybe some source also will be extracted from the background. We expect to see of the order of 100,000 sources in our galaxy to answer questions like how these binaries are forming and evolving. They are mostly wide dwarf binaries, but there will be a contamination of double neutron star and double black hole systems. And also we would like to constrain the type 1a supernova rate. Soon after the discovery of 1509-14, Alberto Cesana said, well, but since any coalescing binary is a low frequency source when it is far from coalescence, he just put this binary in the LISA sensitivity curve and noticed that it could be detected and it could sweep through the LISA band to merge into the LIGO sensitivity range. And this opened the possibility of having an unexpected new type of sources that will be used to send alert and to learn more about rates. Here I'm showing just the path that these binaries are traveling. Here we see the inspiral, and then we will see the merger and ring down. But I take the opportunity to show again strain versus frequency, because here I'm showing the sensitivity curve of Einstein telescope and of Cosmic Explorer with my arrow, that are the third generation ground-based interferometers that will be probably there when LISA will take data. And so we might have a synergy. Another class of very interesting sources are the so-called extreme mass ratio inspirals. So imagine you have a little stellar black hole which is orbiting around a massive black hole like a Milky-Way black hole of 10 to the 6 solar masses. Again, in the characteristic strain versus frequency space, we see here indicated the harmonics of the motion of this little black hole. MRIs are characterized by highly relativistic and generic, mildly eccentric orbits. So you imagine you have a bee that is around this black hole, and this is a way to probe the space-time structure around the black hole. They stay in band for several years, and we do hope to see the plunge when they cross the horizon, so the absence of any signal once the horizon is crossed, and they display extreme forms of precession, lengthening out of the plane and in plane. So, as I told you, they are magnificent sources to explore the multipolar structure of space-time around stationary black holes, because we will have the ability to measure the quadruple moment of a black hole to a precision in 1 part to 10 to the 3. For these sources, the masses of the black hole, the spin of the black hole will be measured with an absolute accuracy of 1 part in 10 to the 3. So we could really test the Noether theorem that is stating that according to general relativity, space-time is uniquely determined by the mass and the spin of the black hole. So we are really probing the space-time geometry, not only seeing the event horizon. We can really have a map of the space-time. And this will be unique, because I remind you that when LISA will fly, 04 and 05, the run on Earth, will have detected coalescences of stellar black holes, and from the ring down, the oscillation of the newly formed black hole, we could also infer whether the Noether theorem is valid or not. But, you know, here we have 6 orders of magnitudes in mass scale, and we don't know whether the black holes that are in the midst of a galactic nucleus are Kerr or even could be more exotic objects. So as far as these sources are concerned, we would like to know really to probe the space-time, but from the dynamical point of view is very, very interesting, because in order to produce these very relativistic sources, we have to know how stars and stellar black holes from the gravitational sphere of influence of the massive black hole plunge and come swiftly very close to the horizon due to relaxation processes at distances of several fractions of a parsec. So it is very interesting from the dynamical point of view discover these sources, because also the rates of these events are uncertain. We could have 10, 50, but knowing LISA will measure the rates, and then we will have access to knowledge on the dynamics of relaxation in galactic nuclei. And then we have coalescing massive black holes, my favorite topic. Again, here you see in this Fourier domain, the signal that is getting very, very loud is increasing in frequency. where you see the peak, we have the merger, and then the ring down. These sources are transient sources that can stay in the LISA band for roughly a month, a week, days, depending on the mass and on the redshift. And here I'm showing what we call the waterfall plot to demonstrate that LISA cosmic horizons for massive black hole is almost the entire universe. Here I'm plotting in the plane cosmological redshift versus mass in the rest frame. This line, I'm sorry, it's relatively weak, but these are lines of constant signal to noise ratio. So let me just show this line. Within this range, all sources will be detected with an SNR in excess of 30, in the middle 100, and at very low redshift, we can have a source with an SNR of 1000. What it is relevant to notice in this plot is that LISA will be sensitive mostly to black holes with a mass, a total mass between a few times 10 to the 4, up to several times 10 to the 6, up to redshift 15, but even 20 if they exist. So we can pierce deep into the cosmic dawn, we can cross the reionization epoch and have also a knowledge of this new population of binary black holes at cosmic dawn. The idea is that given the way structure and galaxies are forming, growing, and assembly, black holes appear to inevitably cross this bandwidth, and the information we gather is complementary to the one coming from electromagnetic observation, because this area here is just the area of knowledge of accreting black holes that I got from this paper. So the best knowledge we have today of accreting black holes in galaxies. So you see the complementarity, because we mostly see very massive black hole. LISA will instead detect the lighter one. Just to give you a cartoon, the hope is just to detect merger at very high redshift to learn about what we call the seeds. You know that there is a population of high redshift quasars. Most of the people here in this audience are really leading scientists in this field. So we have these black holes at redshift 7 when the universe is less than 1 billion years old, and they are already very massive, and we know also that the bulk of the population has grown by accretion, and so it is clear that black hole comes to birth lighter and gain mass through accretion and to a minor extent to merger. And so this has led to the hypothesis that a supermassive black hole are growing from seed that are forming in the very high redshift universe, either, and I mention some of the mechanisms. So we would like to detect these 10 to the 4, 10 to the 5 black holes that would be too dim to be detected with electromagnetic observations. And since the measurements of the masses and spins are really extremely accurate, we have the possibility of measuring the spin for the entire population that we are going to observe. And the spin is a quite important parameter, because it is affected by merger. In general, it is increasing after a merger, but when you accrete for many, many order of magnitude a lot of mass from an accretion disk, the spin can be either aligned with the accretion disk, but it can also warp and change direction if the feeding is occurring on different planes if accretion a la King, we say, is not coherent, but it is randomly oriented. And this is very relevant. A cartoon to depict the black hole growth from seed. We have many models, and it will be still, I believe, very difficult to select a given avenue. So the seeds of the black holes that are feeding the high redshift quasars could come from primordial black holes that are extending over a wide range of masses. So it means that the black holes are present before galaxies are forming, or the seeds are either coming from the first stars or from runaway collision of stars in nuclear star clusters that are in any case forming in the first forming galaxies. Or a very popular model is the so-called direct collapse black hole. So imagine you have a cloud of gas of very low metallicity, which is illuminated by a Lyman-Werner UV flux, which is preventing the cloud from fragmenting. And so you force the cloud to go through an almost direct collapse after a phase, a very brief phase of hydrogen burning. And so depending on the environment, on the gas reservoir, you might have a fast growth to explain the high Z quasar, but you can have a slower growth to explain maybe black holes as the one hosted in our Milky Way, Sagittarius A star, which has the mass that typical LISA will detect, or the slow can be very, very delayed. And so maybe we can have the black hole of 10 to the 4 or 10 to the 5 solar masses that inhabit dwarf galaxies. Rates are very important to know, and we discovered that they are depending on the seeding model, on the accretion history, and on dynamics. The dependence on the seeding model is indicated in this figure. If you imagine that the population that is providing the seed are only light seed coming from the very pristine stars, well, the position of the sources is in this blue area. If you believe instead that the dominant channel is that of heavy seed, the direct black hole collapse, then observation will be skewed to higher masses. And also the rates are depending on the fact that when you have two halos that are merging, the two black holes can have a chaotic dynamics or irregular dynamics. And in order to reach the domain where gravitational waves are driving the inspiral, from the kiloparsec merger scale, you have to take the black hole down to the sub-milliparsec scale. And so you need the action of stellar and gaseous torques to break to break their orbits and drive them closer and closer. So, and we have uncertainty. This is introducing the notion of time delay distribution, as it is also for the case of stellar binaries. And if the delay times are distributed over a wide range from, say, 100 million years, but also several giga years, this is going to affect the rate. The longer is the delay in time, we see merger at closer redshift, but we lose the high redshift ones. So as of today, the rates in conservative models are between 2 and 20 per year. So we hope to detect a decent number of black holes to have sort of, to infer some statistical properties. So the key question we are answering with the massive black holes are, when and do seeds form and grow, how massive black holes are growing. The spin is a measurement which is relevant, and we know that it is very difficult to measure the spin of an accreting black hole. Here we have a new tool to access to this very important parameter. And I would like really to know if there is this physical deep link between the black holes that are forming from stars and the supermassive black hole. And there are no boson stars or exotic objects. Already, as you know, the shadow imaging the Sagittarius A star and M87 has led to the discovery of a consistencies of being these dark objects as being black holes. And when you read their paper, they claim that there is no evidence, not for a reflecting surface or an extended solid surface. So they are probably black hole, and in their claim, they say, and I'm very happy that they could prove the universality of black hole, at least on 3 orders of magnitude in scale. But I believe that we can probably cover the entire range. Synergy with Einstein telescope. Here I'm showing the waterfall plot of LISA in blue, similar to the one I've showed you previously, but also we made the exercise to construct also the waterfall plot for Einstein telescope. And the message here is that Einstein telescope will see almost all stellar binaries in the universe up to redshift 20, especially the heavy stellar black holes that can form in low metallicity environment. These triangles, squares, and circles are coming from a semi-analytical model we built with Rosa Valiante. I don't go into the detail, but I want you just to catch the flow that is in this figure. So if the seeds are forming from stars, they will transit through the LISA band, and then we can explain the high redshift quasar, the quasar at the peak of the AGN activity, and also the nearby one over a wide range. And we have the contribution from the direct collapse model and from the population tree. So these are not contemporary observations, but we can infer statistically the different weight that the different population can provide. And so through a Bayesian analysis, one could say that you would be in favor of an heavy seed or a runaway black hole formed in nuclear star clusters. So this is really the hope. And if there will be outliers, in the sense the discovery of a merger at redshift 18 of 10 to the 5 solar masses, then we know that the seed has to be really heavy, but we cannot exclude other origins. So if I have 5 minutes, can I have 5 minutes? So let me just show first the simulation we carried on in Milano. Here you see 2 merging black holes embedded in a hot magnetized clouds. There are shocks that lead to accretion to the black hole before they are merging. And then you see the recoiling black hole, which is surrounded by a magnetized disk. So it is clear that the science return of coincident gravitational and electromagnetic wave observation, no question, will be immense, because for the first time we can, well, not for the first time, we can, in the domain of physics as cosmology, have a measurement of the speed of gravity at cosmological distances if we detect an electromagnetic counterpart out of redshift 3, because the gravitational wave, as you know, contains a measurement of the luminosity distance. And if we see a bright electromagnetic counterpart, we identify the galaxy, we measure the redshift, and so without the need of a cosmic distance ladder, we can measure the expansion rate of the universe to a precision which is less than 10%. But as an astrophysicist, it's very interesting to detect the accretion light, the light that is coming from accretion in flows that are violently changing during the inspiral, and to detect the merger and the post-merger emission with a very unique ability to inform electromagnetic telescope that we are seeing a binary with this mass, with this component masses, with this spin, with this luminosity distance, and with this sky position. But we have a priori physical information that can be done in real time. The only drawback is that, as of today, we do not have any evidence of transient-like emission that could be attributed to a merger event. And little is known about accreting black holes that are low mass, 10 to the 5, 10 to the 7, bolometric correction, spectrum, time variability, level of obscuration. And so we have to rely on theory. And there has been a large effort in the last years to understand how accretion is arranged around two inspiraling black holes. And it has been discovered that the black holes are excavating a cavity due to its gravitational quadrupolar torque, but in reality the cavity is filled of material and filament of enough angular momentum that they can create mini disk. And this could be sort of a light curve in the precursor phase, in the merger phase, with structure and periodicities which are the fingerprint that we are going to see, not a variable AGN, but a merging binary, with a spectrum that can go from optical to X-rays. When you have formed the black hole is receiving a recoil because gravitational waves are carrying linear momentum, and depending on whether the kick is within the disk plane or perpendicular, you will have different perturbation and shock features in the accretion, the circumbinary accretion disk that can emerge several months and are weak. So the other possibility, since a merger is producing a black hole with a high spin, is to have a jet. And we see in all the simulation the launch of, so the condition for launching a jet. And then you could emit a broadband emission similar to what is a gamma ray burst. And so you would expect that you see in the pre-merger phase an active galactic nucleus that probably is already on years or century before, and then a jump in the luminosity in the interaction with the circumbinary disk. But how this universe, how large is the interaction in between these two universes? And unfortunately, we are understanding that is not very large, because LISA ability to localize a source is fine at merger, but it is a bit difficult in the inspiral phase. Here I'm showing, I don't have to go into the detail, but just to give you two numbers. During the inspiral phase, the sources at redshift 1, regardless their mass, they can be localized over 100 square degrees or even more. And the field of view of LSST and Athena are too small, but luckily when the merger is occurring, we know also how to handle the waveform in the right way, so we can have a large fraction, or so these are a distribution of sources. Some sources can really enter the field of view of Athena, some also at the level of arc minutes. But they have to be very, very nearby. And also we discovered something that was unexpected by using Bayesian analysis, that some sources are not just there in one point in the sky, but they show multimodality. So they can be somewhere else symmetrically in other places in the universe. And this multimodality is broken only at merger. And so the message is let's wait until the merger is occurring and then send alert. So we decided to create a mock universe and study how many galaxies, in any case, I have in the field of view that Lisa is providing me, and have Athena, or a downgraded Athena with 10 arc-second resolution in imaging, and links. Here is the last two slides. We are at merger. We have a binary of 3 × 10⁶ solar masses. The red dot is the true binary where the merger is occurring. And in the optical, there are around, within delta omega of 0.77 square degree, the source is a redshift 2, we have several thousand galaxies. But if we use and select the field by looking in the X-rays, using the luminosity function we know of the AGN today, we have found that for this binary, we have to decide among 70 AGN that are in any case louder than the truth source, for which we know everything except the accretion rate, which is the only parameter which is uncertain. And if we have as reference sky E Rosita, there won't be many AGN from E Rosita because they are too loud. Instead, we have still smaller, lower, weaker AGN compared to our source. But the point here is that the risk is to either not have time, to enter the confusion limit. And so this makes really challenging. If we have a slightly lighter source of 3 × 10⁵ solar masses very nearby in our backyard, it is still luminous because it is nearby. And then in the LISA field of view, we have little less galaxies and only few AGN. And so this is promising, but we have really to learn how these, the bolometric correction that we have to apply to these low mass active galactic nuclei. So in a nutshell, I think that X-ray selection of counterpart is key to reduce the number of potential host candidates. If you have reduction of the imaging power, then you are in trouble with the confusion limit. Links is far rapid in detecting the electromagnetic source because of its enhanced sensitivity, but it has a smaller field of view. And so we need more pointings. And only light binaries can really be detected and have joint observations. And so I thank you very much for your attention. Leaving here.
So thank you, Monica, for the very nice and exciting talk. And so if we have some question, I think she's happy to answer. So please, don't be shy. Carlo.
Thank you so much. So apart from the individual sources in the universe detectable by LISA, so I was wondering if you can have cosmological information from the background of gravitational waves that are expected, because anyhow there will be a background.
Yes, yes, it's a very important remark. I'm not an expert, I'm not a cosmologist. And when I met my friends that are cosmologists, it is really a different language. I don't have the culture, but I prepared the slide. In the sense that we expect to see various backgrounds. First, we are thinking at astrophysical backgrounds coming from stellar black hole binaries, because we didn't expect so many, and they are. And this could be the level, according to a model we built with relatively massive black holes in the plane, the energy density versus frequency, that could even hamper the detection of extreme mass ratio in spiral. And there is really ongoing work. And here I'm showing the figure I grabbed from the living review from my colleagues. There is a lot of interest, and it clearly would be groundbreaking if we could detect a cosmological background from the primeval universe. And here you show, this figure is showing omega, the energy density in the stochastic background versus frequency. Here we have light bird, and that is hoping to detect through the B modes the ratio R, for which only we have limits coming from gravitational waves from inflation. Here we have the pulsar timing array. Here is LISA. Here is Einstein telescope or LIGO or whatever. And the dashed line is the expected background from inflation, which is flat. So he has no structure in the frequency. But for instance, cosmic strings, these one could, if you tune the parameters, could really be detectable by LISA and also by Einstein telescope, depending on the level, which is completely uncertain. Then there is a model of axion inflation, which is can be detected both by the ground and space-based interferometers. So there is a lot of interest and especially a very important effort in devising techniques to extract this background from the noise. LISA, contrary to ground-based detectors, have continuous sources. So we cannot have a time in which we can measure the noise of the constellation even, and there will be always sources around. And the way you subtract the sources is a very, very delicate issue. We call it the LISA data challenge, is the enchilada. And this is the next challenge for the future. With Einstein's telescope, we expect to detect 1 million black hole binaries per year, but they will still be short-lived, that you can sort of listen to the beep, 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 beep of all these sources and maybe some long transient associated to neutron stars. And so here it is a challenge, but there is a real task force within LISA, because we are all aware that that would be the known unknown that would really make LISA a very full discovery space.
Carlo. Okay.
Oh, first of all, thank you for the very nice lecture. So in several plots, you were showing the mass of the binary. I didn't get whether this is the total mass or if you are assuming something about the mass ratio. How does the mass ratio change this kind of diagram?
Very nice. No, in all the plots, historically, but also because I have to go up. In all the plots, we have the total mass of the binary in the rest frame. But for instance, here where, oh no, I have to go up. We let the ratio, the mass ratio vary. In general, because of consideration of dynamics, when we have a major merger between two massive black holes, we expect that they reach the gravitational domain where they can merge when their mass ratio is between 0.1 and 1. And the waterfall plot of these, so the SNR is decreasing. So you are losing, if you increase the mass ratio, you reduce the amplitude of the wave because the amplitude is scaling also with the reduced mass, and you lower a bit, but it's never critical. And through the parameter estimation, we are getting the last figures of merit for the Red Book. For all sources below redshift 7, the mass ratio can be determined with an uncertainty of less than 10%, even 5% or less. Spins very well determined. So we learn, but by match filtering the waveform with the data.
Ciao Monica.
Ciao Filippo.
Very nice talk. And the sensitivity is really exceptional. But my question concerns the localization capability of the instrument, in the sense that when you have a very high sensitivity, this has been accompanied by an angular resolution. Otherwise, you go in the, it's impossible to distinguish between different sources. And the capability is there.
Yes, in fact, concerning sky position uncertainties, except at merger, only the very nearby, if you have a nearby light binary, light means 10 to the 5, which stays in band for a month, then you can exploit the motion of the constellation to get the delta omega, the error, which is not in this figure. And here the uncertainties are not only related to the Laser antenna pattern, but here we are simulating population varying the spin and the mass ratio, because when you go in the sky, you don't know which is your the mass ratio of your source. And so we did a statistical approach, a family. And so the sky localization, we thought it was better. It is not as we were willing. And we discovered that, especially at merger, this is a good news, there are higher order harmonics that are entering the waveform, which are breaking degeneracies and really helping us maybe also to localize a source within the Athena field of view. But ironically, what is happening is the following. The sources that are really well localized are super loud in gravitational waves, but are super dim in X-rays. And so there you have the problem of the confusion limit. And it's sort of a compromise that we have to choose. And we don't know also how many mergers are surrounded by gas, though usually say, of course, there are merger, there is gas, it's going down. Yes, it's going down to very small scales, but you have to go down to the microparsec scale, and so it's not obvious. But LISA is what we have. I don't know whether I understood exactly your question, or...
Roberto.
Hi, beautiful talk, and thanks. I was wondering, so every time you mention a merger of massive black holes, especially for the reionization epoch, there's a lot of astrophysical uncertainty that goes into that number.
Infinite.
And I think there are a number of constraints that, especially in the next 5 to 10 years, we can get from observation in terms of the typical halo mass of the high-Resh quasars, or the demographics of the smaller mass black holes, the merger rates. What do you think would be the most critical parameter we can get from observation that could help your estimates?
I think that it is the morphology of the galaxy and the density, the stellar profile and the gas density. And because when you simulate galaxies that are spiral with their bulge, and you take a Search's profile for the stellar distribution, you are happy, and you can make some analytical estimate. But you don't know what is in reality. We did a lot of simulation. For instance, we considered as you know, you have two black holes in a disk, and the disk is clumpy because it is forming stars, and clumps can sort of act as scatterers of the dynamic. So we might lose a potential binary. So I think that the morphology and the stellar profile will be very relevant. I'm glad you asked the point that I want to make, because when we prepare a science case, we have to sell the science case. But we have to think that LISA will come in 2037, and JWST will uncover the uncoverable. So we might see, I really would like to see black hole of 10 to the 5 at below the redshift of reionization, because the abundance of these black holes can also tell you about the seeds. So I think that we will learn about seeds not only in synergy with ground-based detectors, but in synergy also with all the electromagnetic observations on the AGN you are studying. And you hope you will find the one at redshift lower than 7, because as far as I understand, they are not visible. And in the new data of JWST, there is no evidence of any AGN, because unless they are very overmassive for the scaling relation applied to their galaxies. And but we will know a lot. And so we will change our science case.
Yeah, I think we have a question from home. Yeah, there is another question. Say quick, sempre estimate.
For question, you have 2 mirror error boxes when you localize it, because you have only 3 masses. If you had 4, one outside the plane of the other 3, you would get a solution.
No, sorry, I couldn't really understand the mirror.
When you get the localization,
Yes.
you have a real location and a mirror one.
Yes, yes.
That is because you have only 3 masses.
No. It's related to the way you perform the analysis, because there are a lot of degeneracy, inclination versus luminosity distance, spin and eccentricity, and polarization, and the orientation of the plane of the binary relative to the line of sight. So there's a lot of degeneracy that you can hope breaking, and the discovery of these multimodality has come very, very recently, and it is related to very delicate symmetries that are when you expand in spherical harmonics the waveforms and try to do the analysis. Is not related to the instrument, is related in the way you perform the analysis.
Martin Topinka, thank you for the beautiful talk. Could you repeat, please, what features you plan to observe in selecting galaxy candidates by Athena?
The feature of the candidate galaxies.
In selecting galaxy candidates by Athena.
What we did, or what? Well, I can comment. Well, when we constructed our mock universe, the semi-analytical model coupled with the Millennium simulation has been tested to luminosity function and so on and so on. And the AGN we put there are AGN according to the luminosity functions we expect at that redshift. Concerning the host of the galaxy, we are discovering, because we have also this mock information, all our black holes are living in dwarf galaxies, and where it will be very difficult to find any sign of a merger. And also you have nearby, we are discovering that we have nearby galaxies having also features of merger, or that had merger, but they are not the one. So the morphology selection, I think it is almost impossible, if that was the question.
So unless there is a very urgent question, I think we can close. Let me thank all of you, Monica, of course, and Francesca, Tatiana, and Enrico, and all the people of the seminars that organized, and Ben, sorry, that organized the meeting, and especially Renato and Alessandro from the first floor for the technical assistance. So thank you very much, and Merry Christmas, Happy New Year if I don't see you. And
Merry Christmas to all of you.